My dear students of 12th Science, in my previous physics class, we discussed there about Faraday's law of electromagnetic inductions as well as Lenz's law. Student, today we want to know about the motional EMF. What do you mean by motional EMF? Whenever the EMF is generated across the conductor or loop due to the motion over the magnetic field is known as motional EMF. First, we want to derive an expression for motional EMF across a straight current carrying conductor which is moving over the magnetic field. Now see the situation. Here we consider a straight conductor AB of length L is moving with a velocity v over the magnetic field. Here the magnetic field B is perpendicular to the whiteboard and directed inward, means the motion of the conductors occurs here perpendicular to the magnetic field. Okay, so as the conductors is in motion, the electrons present in the conductors are also in motions over the magnetic field in a perpendicular direction. Means this magnetic field creates some force on these moving electrons. According to Fleming left hand rules or right hand rules, the force acting on the electrons from the end A to the end B. So that's why at the end B there will be an accumulation of electron. At the end A there will be a deficiency of electron. That's why the end A becomes positively charged and the end B becomes negatively charged. Means across the two ends of the conductor there will be a potential difference comes into play. If we connect these two ends of the conductor by a U-shaped conductor, a current start flowing in these specified directions. Let I be the current pass through these conductors from B to A. And also we know that whenever a current carrying conductors is situated over the magnetic field in perpendicular manner, then the magnetic field is also creates some force on the current carrying conductors, which is ILB. So therefore force acting on the straight current carrying conductors due to the magnetic field B is given by ILB. And according to the Fleming left hand rules, we can identify the direction of this force. Now see the alignment of my left hand. So this is the alignment. So first finger point towards the direction of magnetic field, middle finger along the direction of current, then thumb gives the directions of force on the straight current carrying conductors. So therefore force acting on the straight current carrying conductors in these directions. So against this force, if we want to move this conductor towards right, we have to perform some amount of work done. So therefore for the small displacement dx of the conductor AB towards the right against the force F, the amount of work done is dW is equal F dx is equal, what is the value of F? That is ILB into dx. And what is the definition of I? dq by dt LB dx. Now we just rearrange this expression as dW is equal BL dx by dt into dq is equal BL, and dx by dt is the definition of velocity. So therefore BLV dq. Now dW by dq is equal BLV. By the definition of induced EMF, the induced EMF is given by E equal dW by dq. So therefore from these two expressions we can write E equal BLV. So this is the expression for induced EMF across a straight conductor of length L moving with a velocity v over the magnetic field whenever motion takes place perpendicular to the magnetic field. Now student, if the R be the resistance of this circuit, then the magnitude of the current is given by I equal EMF by resistance is equal BLV by R. Okay. Now if you want to determine the magnitude of this force, so therefore force is equal ILB. Now put the value of I from the previous expression, that is BLV by R. So therefore the force becomes B square L square V by R. Now if you want to determine power required to pull the conductor AB to right with a velocity V, power is equal force into velocity. So therefore force is B square L square V by R multiplied with V means B square L square V square by R. Now student, all this formula, the formula for induced EMF, the formula for current, the formula for force and the formula for power, all these four formula are very important for your numerical purpose. Now we want to derive the expression for motional EMF whenever a loop is moving over the magnetic field. Now see the diagram very carefully. Here we consider a magnetic field which is perpendicular to the whiteboard and directed inward. Okay, so now initially a rectangular loop ADCB is situated over this magnetic field. Whenever the loop is at rest, then the magnetic flux linking with the loop is constant, means there will be no induced EMF. But whenever some portion of the loop moves out of the magnetic field, then the magnetic flux linking with the loop is changes, by which there will be some induced EMF. Now see, the loop is moving with the velocity v towards right. Okay, so therefore area of D dash C dash is the area which is move out of the magnetic field. So that's why area of the loop move out of the magnetic field, dA is equal length into breadth. What is the length? I consider this is L and breadth is dx. So therefore area move out, dA is equal L dx. So therefore decrease in magnetic flux, as the magnetic flux decreases, that's why I write minus d phi b equal B into dA according to the definition of flux, or minus d phi b equal B and dA means LdX. Now the rate of change of magnetic flux, that is minus d phi b by dt equal B L dx by dt, and dx by dt means the velocity of the loop. So therefore B L V. Clear? So therefore according to the Faraday's law, we know that minus d phi b by dt is the induced EMF. So therefore E equal minus d phi b by dt equal BLV. So therefore induced EMF across the loop is also BLV, which is same for a straight current carrying conductors. Now while the expression is same for the induced EMF of the loop and the straight current carrying conductors, you have to know. See the diagram very carefully. Here the loop consists of four conductors AD, DC, CB and AB. Now for the conductors AD and BC, the electrons are not moving along the length, they are moving along the breadth of the conductors. That's why for these two conductors there will be no induced EMF. The conductor DC moves out of the magnetic field here, so therefore the induced EMF for DC is also 0. So only the induced EMF in the loop exists for the conductors AB, which behaves as a single straight current carrying conductor. That's why induced EMF here also E equal BLV. And the directions according to the previous case, this end becomes positive and this end becomes negative. Clear? Now student, lastly we want to derive the induced EMF whenever a bar is rotating in a magnetic field. Here we consider a magnetic field which is perpendicular to the whiteboard and directed inward. On this magnetic field, a bar of length L moving with angular velocity omega about a pivoted point O, So as the bar is rotating over the magnetic field, the magnetic flux linking with the bar is changes. That's why an induced EMF is set up across the bar. Now to determine the expression for induced EMF, we consider a small segment of length dr at a distance r from the pivoted point O, which is moving with a velocity v. So according to the formula of induced EMF, the induced EMF of the small segment of length dr is given by d epsilon is equal bv dr. bv dr. Compare with this equation bv dr. Here L is the dr, that is the length of the small segment. Now there will be a relations between V and omega, and the relation is V equal R omega. So therefore d epsilon is equal B omega R dr. So this is the expression for induced EMF only for the small segment. But our aim, we want to determine the induced EMF for the whole conductors. So therefore we have to integrate this equation, where the integration limit is from 0 to L, means R is varies from 0 to L. So therefore E equal B omega integration 0 to L R dr, or E equal B omega. The integration formula of this is R square by 2, lower limit, upper limit. So this gives only L square by 2. So is equal half B omega L square. So therefore induced EMF across a bar of length L rotating with a angular speed omega over the magnetic field B is given by E equal half B omega L square. Now in terms of frequency nu, the induced EMF becomes E equal half B omega, means 2 pi nu L square. 2 cancel, so E equal pi B nu L square. Now student, read all this portion very carefully. This is very important portions of the chapter Electromagnetic Induction. Lots of numericals comes in your questions paper from this portion. Thank you.